Welcome everyone to the second discussion session of this 3 weeks LLM bootcamp offered by Pathway in collaboration with DevClub IT Delhi. So the purpose of this discussion session is to go through the modules that we have and know if you have any doubts or if you have any ideas to share while you go through this content. So few days back, Shaurya covered the topic of basics of LLMs, and today we will be starting with word vectors. So the contents of this module were that we have what is a word vector and how are the relationships between word vectors defined, what is context in LLMs, and we'll be also going through the architecture of transformers and the attention mechanisms. So let's get started. I'll go through the whole module briefly, and you can chip in at any point if you have any doubts or if you want to share any cool stuff that you found while reading this. So you can just chip in, unmute, and say whatever you want to. Audio is quite low. Okay. Am I audible now?
Yeah, it is doable actually.
It's
Audio,
doable.
yeah.
Okay. Sure. So let's start the session. Uh, okay. So, what is a word vector? So, what comes in your mind when you hear this phrase, word vector? Can anyone unmute and speak? Um, sure. Okay, I'll go ahead. So, word vector is basically a way to represent a word numerically. So, we need to understand that uh, LLMs are machine learning models, and machine learning models work on numbers. And the way we interact with language is via words. So when we give words as input to the LLMs, they first convert it into numbers. So one way of doing that is word vectors. So what does it say? Imagine language as a vast multi-dimensional space where each word has its unique spot. So word vectors convert word into numerical format, making text comprehensible to LLMs. So this video also discusses this, like what is the intuition behind converting words to vectors, right? So what we want is that we want to convert the words into an n-dimensional vector space where the meaning of the words is preserved. That is, that similar words have similar vectors, and the grammatical and semantic information is also stored in that space. So we'll see how that happens. Word vector relationships. Yes. Uh, okay, we'll continue. So word vector relationships. So navigating the landscape of text representation, it's essential to grasp how words relate to each other in the vector form, right? So this video explains that how are the words related in that vector space. So I'll show an example also. So what this video also explains the advancement by Google's Word2Vec project. So Word2Vec is an embedding model that basically a model that converts the words into vectors that we're talking about. So Google did this in 2013, where they trained this model on the news dataset that they had, and they observed that the intuition that we have in English language by grammar, that is being replicated in the vector space also. For example, we know that if we see this, king minus man plus woman. So if we subtract man from king, we are left with the royal part, and we add that royalty part to woman, then we get queen. So if a human reads this, then we can understand that this makes sense. Now, for that vector representation also, they found that when they take the vectors of these three and apply these operations, they get a vector which is very close to the vector of queen. So this means that we were going in the right direction while converting the words into vectors. Okay. So this video further examines how word vector relationships contribute to similarity searches, a crucial function in LLMs. Uh, yes. So we have a example of a demo of seeing these words in the vector space. So this is a CMU website. So we can see that they have plotted the words in their embedding space, which they learned in their LLM models, and the feature space is 300 in size, but here they have chosen the important features as gender, age, and the residual features in this. So here we can visualize. Pardon, can you speak again?
I think that was a mistake.
Achha, okay, sure.
Mm.
I'll continue. So let's try to visualize that relationship here as well. So let's see this. If we take king and we subtract man, so we have the royalty part left. And if we add woman to this, then we expect to get the vector of queen. So let's see what happens here. See, so we get a vector which is very close to king. So here what it did is that it applied simple vector arithmetic. When we go from man to king, uh, basically this is the difference vector between king and man. And when you place it at women, it is closest to the queen point. So this is a very strong representation of the language that we have in a vector space. Here you can also play around with other features such as royalty number, tens. So tens basically you can have walk and walking. So they will also be related in some manner. Yes. So the terms vector embeddings and word vectors are often used interchangeably when discussing LLMs. So vector embeddings means that you are taking that word and you're embedding it inside the n-dimensional space. So these mean the same. Now these embeddings are stored in vector indices, which are sophisticated data structures designed for fast and accurate retrieval of information based on these embeddings. So now what we want is that we want to convert the words into these vectors. And when the transformer has done its computation, we want to convert back these vectors into words. So these two operations need to be fast for the LLMs to be effective. So this is done via these vector indices, and there's a whole lot of research going on in these databases as well. So we can see that these platforms cater to such features. So Pinecone, Viviate, ChromaDB, and so how to choose the right vectors embedding model? So we know that the GPTs are evolving. So we had GPT-2, then we had GPT-3 and GPT-4. So they improved. Similarly, the vector embedding model can be thought of as a unique unit inside the LLM, right? So these are developed independently by researchers, and we can see that they improve performance, and there's a leaderboard on the embedding model itself. So we can see the MTEB leaderboard, and we see that there are different embedding models developed. And here's the overall ranking. Here are the different functions, basically specialized models. And we see that they are also ranked on some metrics, and these are also competing among themselves. And as we get more and more better embedding models, the LLMs will automatically become better. So whenever you are working on some project, you can go to this website and see which task are you working on and choose the best embedding model for a project. So this was mostly about the word vectors and embedding. So now we'll go to the second important part of the whole LLM pipeline, which is the context. So what is context? Can anyone say what context means when I say in language? What is context? What comes in your mind when you hear context?
Give some information about like elaborate on what we want from our LLM, like give some background information about your task. Elaborate
Yes,
on
right,
that.
right. So if I give you a sentence in English, so what is context in that?
I think context regarding the information.
Context regarding, yes, regarding the information.
Like
Basically,
a brief
It is the
description of
word.
the whatever we want to know, like brief description about a topic.
yes, yes, that's right. So basically, we want to give a brief description encompassing the whole information. So it's like a summary of the sentence, right? We need to have the right kind of information before we give to prompt to the LLM. So context can be seen in two ways. So one is that when you give the prompt to LLM, there should be proper context in the input, right? That is one thing. And second, the LLM should be able to take that context while it's making its computations, right? So here the example is given like what color is apple? So it gives an answer which is according to fruit. But you were expecting an answer about the company. So in this case, your prompt is not complete context wise, right? So instead, if you had written I ate an apple, right? So then the LLM would have used the ate to understand that this apple is being talked about is a fruit and not the company, right? So a technical explanation made simple. Basically, uh, context is like a summary of the sentence, and the context has been understood from the old models that we had, like RNNs. So, and after that, we had LSTM, and now this. So, in general, LLMs like GPT-4 Llama use various techniques to understand context surrounding each word. For instance, GPT-4 uses attention mechanism, whereas older models did not use that. So, we'll discuss these in detail. I have some content for this after we go through this module. So, in a summary, what we want to understand is that whenever we are doing some task, like what does LLM do? We have discussed it earlier also. What is the most basic function of a LLM? Just a one-line answer.
To predict the next word
Uh,
based upon a context.
Yes. Yes. So whenever I give it a text, I want to predict the next token, right? So there should be a context of the whole sentence while it's predicting that token. It's not about just looking at the last word. It's about looking at the whole sentence to predict the next token. So that is context, and we'll come back to it later. Let's see what we have next. So transforming vectors into
I
LLM
had a question.
response. Yes, yes. Go ahead.
Yes. So suppose there is a word apple and it has two
Yes.
meanings. So are there two different word vectors in the n-dimensional space, or is it a single vector that points to that word?
Okay. Um,
I think it may be single.
I think it can be like the vertical with the average of both the meanings. And depending on the rest of the countries, you can find out which meaning is there.
Okay.
thank you, Aditya. So I think it's clear now. So now moving on to this, transforming vectors into LLM responses. So now we are familiar with word vectors, and now we know that whenever we give some input to LLMs, it first converts into words, and these words are converted into vectors. Then it processes in vectors terms only, and then we get words back. So converting into vectors, before that, there's a process called tokenization, right? So first, we have the sentence with us. So consider a tokenizer as a sentence divider. Its job is to dissect the sentence into smaller fragments, such as words, characters, subwords, symbols that a model can process. So uh, there are multiple ways you can tokenize a sentence. For example, consider this sentence itself, right? What all ways you can think to tokenize this? Break it into smaller parts. What all ways can you think of? Anyone can speak about this.
Like by just dissecting each word.
Yes. So you can just take up the empty spaces and break the sentence into simple words. That is one way. Okay. Other way is that you find sub phrases in this. You say, okay, word vectors is one thing, significance of context is one thing. Okay. Fundamental components one thing. So this is called subword tokenization. Another tokenization is that you tokenize the whole sentence itself. Okay, there are multiple ways to tokenize. So tokenizer is in itself a good number of techniques are there. Okay, so it yes, the specific approach varies depending on model size and design. Conversely, detokenizers perform opposite operation. They assemble the pieces output by LLM into coherent sentences. So this video explains how a prompt is processed by a LLM. So while the underlying mathematics might be complex, the main objective remains simple: predicting words. So the video, yes. So let's. It's a large video. I'll go to the main part of it and explain what he's trying to say. Yes. So yes. So look at this. Now prompt. There's a prompt we are giving to the LLM that once upon a time, right? And now I want the LLM to complete this this thing. So what happens first? First, we break this down into tokens. Let's say those are the individual words, and then the LLM uh, attends basically infers a context from that. We will learn about how it infers that, but let's say it infers a context from those 4 words. So that context is stored here. Now we want it to produce the next token, right? So the LLM now will use that context to generate the next token. So it uses that. We'll see how that works as well. But let's say the next word is there. So now it has these 5 words, and now it wants to predict the next token. So what it does is it again and takes out what it does. It has once upon a time. It predicts there using the context that it had previously, and then it again encodes there into its embedding space, infers a new context of upon once upon a time there, and then continues to produce the next word in the cycle. There was, right? And this goes on. So what it does is it has original context, produces one word, encodes that, makes a new context, then produces next word, and it continues. Right? So this is how it works. Now, how is it inferring the context? That is done in multiple ways. So one way is attention mechanism. So now that you understand the role of context, you might want to grasp some context to appreciate how these models work at a granular level. So these are bonus resources. You should go through this. Also, tokenization is a vast field, and this paper is the fundamental paper on attention. So this is also very interesting. You can go through this and develop your understanding. And yeah, so this is the bonus section which explains the working of transformers. I'll shortly go through some parts which will make it easy to understand for you. So first I'll go through RNN. Right. So RNN is a model which is precursor to transformers. So before transformers, we have LSTM, and before LSTM, we have RNN. So RNN, basic function of RNN was simple. You have given a sequence, and now you want to produce another sequence. So can someone give me one example problem where this kind of modeling can be done? Any problem where we have one sequence and we want to convert it into another sequence of words, let's say sequence of words.
Can active voice into passive voice be counted as this part of converting same thing into another form of sequence?
Yes, it can be. It can be taken. You can give this prompt to ChatGPT also. Right. This is one kind of task it can do. Right. So when this was done fundamentally, one task that was seen was language translation. So I'm giving one sentence in English. I want to convert it into Hindi. Okay. So this was a sequence to sequence model. Now, how did it work? I'll explain very sort of high level architecture. So how it worked was that uh, you first input the first. Let's say you are converting one sentence, English sentence to Hindi, and the length is t+1. Okay. So first you give the first word into this model, and it has an empty context vector here. sitting here. Okay, and it generates output from that. So it has an empty context, and the first word, it generates the first Hindi word from that information itself. Okay. Now what it does is that now this context passes on to the model. This context passes on, and now you have the second English word coming up. So this context, the old context plus the second English word, gives you the second Hindi word. Okay. Now again, that same context passes. Now you have the third English word and third Hindi word. So what is the importance of this context here? This context is carrying the information from the whole sentence behind that word. Okay. So this was the first basic model of sequence to sequence conversion. Okay. Now, can someone give me some disadvantage or some backdrop, basically drawbacks of this model?
If the sentences are too large, then this will
Yes.
be a problem.
Also, if there's some language which has different ordering of the normal translation as such, if Japanese to English and English to Japanese are ordered in a different way, so it wouldn't be able to have, even though it has some context of the previous words, but it won't be able to give
Yes.
the perfect translation.
Exactly. So both the points are correct. First is that if the sentence is too long, that this information is not uh, cannot be stored in sort of small vectors of size, let's say 32 or 64, right? Flowing as a context. Second is that this has an inherent assumption that the order of words will be same in English and Hindi, but it might differ, and in that case, you might need future meaning also, right? So while generating the second word, I'm not looking at the third and further words, but they might be important in getting the information. So this was a drawback of this model, and then we had a model called LSTM. LSTM had a longer context window, but similar kind of problems were being faced. Okay. So after that, people developed attention model. So let's understand how that works. So this is a nice video by StatQuest. This is the best video I found on Transformers, and which helped me also get this concept clear. So we'll go through this. So this will explain how self-attention works. So all now what we want to do is we want to get the context vector, right? Here the context vector was in a linear fashion going from back to end and developing a context. Here what it does is it creates context vector for each of the words, right? So it's not a single context vector for whole sentence. It's a context vector for each of the words, but it uses complete sentence to generate that. So that because of that, there's no loss of information, and every word is getting whole information, the information of whole sentence. So let's go through this briefly. Is it audible?
No,
Can someone confirm?
No,
not
it's
audible.
Okay, it's not audible. Okay, then I'll explain on.
You
So
can also try
it's saying
sharing
that
the tab, Atul. You can try sharing the
yes,
tab if it works instead of
sharing the
the
tab.
yeah.
Okay, I'll share that. I'm sharing this Windows window only, and I'm not getting option for tab.
So you can just enable sound sharing if that's available.
Okay, I'll try that. Now you should be.
Attention works, let's look
Yes,
Uh,
now it's audible.
at the
okay,
details.
thank you. So I'll start this.
So let's go back to our and go. Let's buy a pair hero. 392. Josh, I don't get it. Values we started with. That's a great question, Squatch, and we'll answer it. Values we started with. That's a great among words. Associate the word it with the word pizza. In general terms, self-attention works by seeing how similar each word is to all of the words in the sentence, including itself. For example, Self-attention calculates the similarity between the first word, the, and all of the words in the sentence, including itself. And self-attention calculates these similarities for every word in the sentence. Once the similarities are calculated, they are used to determine how the transformer encodes each word. For example, if you looked at a lot of sentences about pizza and the word it was more commonly associated with pizza than oven, then the similarity score for pizza will cause it to have a larger impact on how the word it is encoded by the transformer. Bam. Now that we know the main ideas of how self-attention works, let's look at the details.
Okay. So I think till here it's enough. Basically, we want to understand that every word will now have the context from the complete sentence. That is the main innovation. Second thing is about parallelization. We'll look at it now.
Why it is
Yes.
called self-attention? Like attention.
Yes. Self-attention is because the model is giving the model is giving attention inside the sentence itself. So the words of this sentence are attending on the words of this sentence itself. That is why it's called self-attention. What would have been cross attention is that if you have two sentences and the words of this sentence attending on the words of the second sentence, that is cross attention. Self attention is on the same sentence. Okay. So now let's see how it works here. I should be able to explain. Yes. So the problem being discussed
Time.
here. Yes. So the problem being discussed here is that they have a sentence called "Let's go." Okay, and "Let's go," and they want to convert it into French. Okay, so what? I think it's difficult to explain. 1 second. I'll go through this first. Right. So we have understood the sequential nature of RNNs and the limitations. So it's now time to introduce the game-changing world of language processing transformers. So there are two things that it does. First, it breaks the sequential barrier. So unlike RNNs which process inputs sequentially, transformers have the remarkable ability to analyze entire sequences or paragraphs simultaneously. So we've seen this. This breakthrough in parallel processing is major leap forward, significantly speeding up how a model learns and understands language. Efficiency in learning. So since transformers don't have to read in sequence, they can be trained on much larger chunks of data at a time. This parallel processing means that they can learn from vast amount of text efficiently without using powerful hardware to speed up things. Right. Uh, foundation. Let's see what happens. This is something clear. This is also clear. So 1 second. Okay. So now I'll explain how it is working in this. So now we have a first sentence, "Let's go." Okay. And now I want to encode each of these words. I want to encode "let's." I want to encode "go." Okay. So how do I encode "let's"? Let's see how to encode "let's." So first I have a matrix called a query matrix. So first what I do is I get the word "let's," and then I use the embedding that I had. So I had the embedding. I converted into this. So this is the uh, basically two-dimensional embedding representation of "let's." Okay. And now what I do is I have a query vector with me. Okay. So query vector I multiply with this, I get this value. All right. Is this clear? First we get the embedding and then the query. This much is clear?
What does embedding mean here?
Okay. Embedding, we said we learned the word vector we were talking about, right?
Yes.
So the other name for word vector is embedding. So we
Okay.
Yes, so we use the word vector of let's, and here the word vector is of 2 dimensional. So this is the word vector of let's. Okay, and now I have a query matrix with me. So just assume it's some matrix. So I multiply this with the query matrix to get a query vector. This is a vector which is representing let's. Okay, it's just another form of its embedding. That's it. So this is a query. So we keep it on one side. And now I have a key matrix with me. So what I do with the key matrix, I multiply this embedding with the key matrix to get key value. So this is the key value for let's. Similarly, I have the embedding for go. So this is the embedding for go. And then I multiply the key matrix to get the key value for go. Okay. So now I have
So what?
query value.
So
Yes,
what
go
are
ahead.
the functions of query and key matrices?
Functions, yes. So function is to get some information that can be compared throughout sentence. Right. So it's like I'm going to see how similar or how relevant are two words. So to encode one word, I might need information from some other words in the sentence. So I'm just getting a test as to which of the words in the sentence is similar to let's. Okay, so for that I need some representation of let's which is comparable with those words. So that representation is query. So I keep the query at one side, and then I get a key for each of the words in the sentence. Okay. So now what we'll do is we'll do a simple dot product between key and query.
कर दो.
Okay. So now what we'll do is we have query for let's and key for let's and key for go. So now what I will do is we'll take a dot product between key and query, dot product between uh, this key and query. So which of them will be higher in this case? Product with key of let's or product with key of go?
पता नहीं कुछ तो हो रहा है. Let's का ही product से ज्यादा होगा.
Let's say होगा. Okay. Kuch doubt? Is there any doubt here? Like if I'm not clear?
लेट्स का ज्यादा इसलिए होगा बिकॉज इट इज अ कॉम्बिनेशन ऑफ लेटर्स, और इज इट बिकॉज क्योंकि उसमें लेटर्स ज्यादा?
Because उसमें let's आया था, so let's is close to let's, मतलब let's is close to let's, वो तो है identically.
ओके.
तो इस हाँ, so dot product is basically similarity score. So when you have two vectors, if they are almost similar, the dot product, what is the dot product? A B cos theta. So if they are all overlapping with each other, then dot product will be higher. But if they are not overlapping, dot product will be less. So here, when we take a dot product, this means that we are testing the similarity. So here, let's is similar to let's, and this will be less. So we get the dot product values, and now we apply softmax on that. So softmax is basically this thing that we are converting that into fractions. So if this dot product was more, we'll give more fraction to this. Okay. So now what I do is I have a third matrix coming up, which is called the value matrix. So what I do is I multiply value matrix with this to get value of let's. I get value of go. Okay. So now what I
Sorry,
had,
sorry, can you repeat again? What did you do to get that value?
we have
The
a
value.
third matrix for the attention mechanism, which is called the value matrix. Okay. So now we simply multiply that value matrix with the embedding that we had to get the value for let's, and value matrix multiplied with go to get the value of go. Okay. Here I had got a weight for each of them. So this weight tells me how important is this word for encoding let's. Okay, this weight tells me how important that word is to encode let's. Now, what I finally do is I take a weighted average of values. So I take this weight, multiply with this value, this weight multiply with this value, and get the final weighted value, which I assign as the attended value. Okay, but is it clear somewhat, or is there any doubt? It will be clear when we once go through the code as well. Okay, let's go through the code also. Okay, so yes, here they have a sentence. Let's see. Okay, so attention mechanism is a scale dot product attention. It involves calculating attention as a sum of weighted sum of values. Weights emerge from compatibility function between query and corresponding keys, formulated as this. So just correlate with what I have explained earlier. So uh, Q is the query value that we have. K is the key, so simple dot product, and we are normalizing it. So what happens is that these values might be large, so you want to normalize it so that these become small and softmax values make sense. Otherwise, these weights go to only 1 or 0, then not much information is getting transferred between the words. So here QK we represent matrices for queries, keys, and values. How do we get those matrices? We'll understand soon. So these matrices are trained. As the model trains, these matrices are learned by the model, and then they remain fixed while we while we test the model. So, but for now, you know that this formula calculates attention as a weighted sum of values, where the weights are determined by compatibility function of the query and corresponding keys. So, query keys values, these are three vectors representing different aspects of the input data. This softmax function is simply uh, getting normalized fractions, like how much of one word should be given is important. Scaling factors we understand. So now calculating query key and value. So first get the vector embeddings. This we understand. So let's say we have this sentence. So we first break down into tokens. Okay. And then what we do is that we use the embedding metrics to find the respective embeddings. So we come directly here. So these are the embeddings of each of these words. Here they are using a 3D embedding space. Right. Now we calculate the query key and values. So here we have the query matrix WQ. So it's initialized randomly, but it's learned over training. So how do you find? So these are the matrices. WQ is query matrix, key matrix, and value matrix. So how do you find the query values? So you just multiply embeddings with the query matrix, right? So this will now have query values for all the words together because it's in matrix form. Here we were talking about individual embeddings and individual queries. So both of these queries, if you have 5 words, all of the 5 query vectors are stored in this matrix because these are matrix computations. So this has all the query values, all the key values, and all the values will be in this. Now, you can print and see also. So there will be 5 here, 5 vectors here. This is the query vector for Manchester and so on. Just to revise this. Yes. Now we calculate the attention scores, taking dot product of query and key matrices. So that is what we were doing there as well. So dot product is divided by square root of dimensionality of k. K is this. So this is something they observed experimentally, that this is a good constant to be used for attention. So they keep this for division normalization. The softmax is applied to convert these scores into probability distribution, 0 to 1 basically, and some of them should be 1. So this softmax function. Are you aware of softmax function, or if someone has doubt in this? It's just the same thing in code. That's it. So the resulting scores are matrix where each element indicates attention score, representing relevance of each word in context of other words in the sentence. That's it. So attention output is you multiply the scores by weights, by values. So this is what is called the self-attention mechanism. So I do this one time. So let's see what happens. Yes, this is a sentence, right? Manchester United hopes to perform better. So when I apply this once, what happens? I get one value vector for each of them, one encoded vector for each of them. Now, when I apply this process multiple times, it gets this. It understands the sentence completely, right? Mm, or let's see what happen. What will happen here? That will be that will make sense. Yes. Let's say we had this sentence. Okay. Now we did the whole attention mechanism here. What will we get? So we'll get one attended vector for each of these. Okay. So now in the first step, the attended vector of this, it will have some information about pizza. Some information, but not all, because this was just one step where we did the multiplications. Now when I repeat that over and over again, this it will have a strong weight of the pizza. So that is in the number space, this it will have been converted into pizza itself completely, right? And which is true also, because it is not making much sense, but if I keep pizza here, it will be much more sensible uh, for the machine to analyze this. That is how attention works. Now, what's the best part is that all of this is happening in parallel. So we just have three computations here. We have just have these computations here. All of them can have happen in parallel. So this is much faster than the RN and LSTM models that we had earlier, right? So this is how attention mechanism works. So transformers, the only important difficult part in transformers is attention only. So now you can read this bonus section to understand transformers. It will be crystal clear. And vision transformer is something. First, what happens is that the transformers gave good results on words. So what the people did was they tried to use the same technique on images, videos, right? So they came up with the vision transformer, and then also they found that they have good results. So you can explore vision transformers as well and use them in hackathons and problems. So they are turning out to be great, right? So that is it from my side. If you have any questions, you can share in the chat, in the WhatsApp group, or here as well. And the first graded quiz is a part of this module. So we encourage you to take the quiz after you go through all these sections, right? And this is important to complete the course. And yes, uh, feel free to share any doubts, fun things you find. So, does anyone want to say something?
Is the dimension of the vector space or the word vector does it depend on the sentence we're analyzing? For example, when we were working on Let's Go, then
Yes.
the space was two-dimensional, and the last sentence that we were doing was a three-dimensional space. So
It does not depend on sentence, it depends on the model itself. So it's upon you to choose what dimension you want for the embeddings. So here, since these are authored by two different authors, so they chose different dimensions for embeddings.
okay, and what exactly does the attention score or value represent, or what does it tell? Uh,
Okay, so it tells you, see, for let's say I'm encoding let's, okay, I have attention scores for all of the words in the sentence. Okay, so there, what is the property of attention scores? First is that each of the attention score belongs between 0 and 1, and second is that all of them sum up to 1. Okay, so it is giving me the information that how much of each of these words is important or relevant to let's. Okay, so this is what information it is giving to me. For example, in this sentence, when I would have calculated attention scores with it as the query vector, then pizza would have had a very high score and not oven. Okay, because naturally it makes sense for it to be pizza and not oven. So it gives us the relevance of that particular word for the query word. That is it.
Okay, understood. Thank you.
Okay, so anyone else want to say something?
Also, do we have to like study those text slides which are
Yeah.
provided, or is it enough
Now that
that
we
we
know the main ideas of how
1 second. My bad.
okay. So
Continue.
how do we like I just wanted to know that should we study that text slides before attempting the quiz, or like we can give it after your lecture only?
I would encourage you to read seriously this also. Like
Okay.
it might happen that there are some missing parts in your understanding or some doubts. So this will just enforce that you are 100% crystal clear, and then you can give the quiz.
Okay. Uh, okay, fine. Thank you.
Anyone else? Okay. So thank you guys. Thank you for attending this session. Mudit, do you have anything to say?
No. I would just like to say that it's interesting that we covered a relatively complex topic with such brevity. So kudos to you, Atul, for that. And
Thank you.
yeah, the quiz does not have, I think, aspects of Transformers architecture, because traditionally, if you want to understand it end to end, it may have a bit more prerequisites. So we really understand that there may be some first, second year students who may be just getting started. So that's why you may not find it in the quiz. If you feel that you definitely want a quiz on that, you can possibly express that on the group or the Discord channel, and we'll see what can be done around it. But yeah. Okay then, cool. I think that's it from my side as well.
Thank you, Mudit. So thank you guys for joining, and we'll encourage you to continue on this journey. It will be really fun. So
Yeah.
thank you.
Can you also
Just
share video?
just one question I wanted to ask. Like at the end of this journey for this like boot camp, like are we going to get to do some kind of POCs or like some kind of mini project or something like that? Or
Yes. There's a project. Mudit, can you expand on that?
Yes, I can. So basically there is so if you look at it right now, what we studied is LLMs. I mean the transformer architecture and all, right? So consider it like understanding the if you consider something like ChatGPT, you understood what GPT is, how it works in a very oversimplified way. Okay. Now, but if you look at LLM application, for example, ChatGPT or any of these, let's say you have to use a GPT kind of thing in a production setting, you'll have to use something called as RAG in most cases. So the project that you'll be building will be using RAG essentially. And yeah, you can, if you're very keen to use a fine-tuned model of your own and then put that along with RAG, pretty much welcome to do so. Yeah, but yeah, it's a mandatory activity, by the way, to build a project by the end of the bootcamp. Yeah, and you need to, yeah, we'll be sharing a few set of resources and kind of problem statements per se, but then it's just for the idea of guiding you. It's not like a hard, it's not like, yeah, that you have to adhere to those problem statements. It's like if you see a problem statement around you that you feel can be best resolved with the help of LLMs, feel free to pick that up. And it must definitely use RAG, that's for sure. Preferably, it should use pathway as well as a part of the guidelines, but that actually technically gives you a lot of flexibility in the sense it's not very restrictive in a way if you look at it eventually. But that is what it is. And yeah, and last element, you need to definitely post it on GitHub as well with a clear README and a demo. That serves two purposes. One is it enables your recruiters to evaluate that project, see the purpose behind it, and make it actually a valuable asset. Otherwise, nobody's going through each of the codes, each of the files on your repo. Second thing is it also helps the reviewing team to review your project. And then they can go through the code if they see the need to do so. But yeah, so those best practices is something that you will be expected to follow. We'll guide you through it. It's not that we expect a perfect outcome from you right away without much guidance from our end.
Okay. Yeah. Thank you.
Thanks.
Okay, cool then. Thank you so much, folks, and good night.
Yeah, thanks everyone.
Thank you.
Thank you.
Thank you.
Thank you,
Bye.
guys.